Okay, so now I'm going to talk about something kind of cool, and that is, how do we predict what charge a given element will tend to form? And we're going to see a pattern here, and this is based on some principles that we already understand. So, the answer is pretty straightforward. If we understand the periodic table, valence electrons, electron configuration, the octet rule, the answer is just kind of staring us in the face. And that is, the octet rule tells us that atoms want an electron configuration like those of the noble gases. So, an atom is going to try to gain an electron configuration like those of the noble gases. Now, as I mentioned, next chapter we'll talk about how atoms can do this by sharing. Right now, we're just going to talk about how atoms do this by straight up giving or receiving electrons. So imagine an atom, imagine, say, chlorine. Actually, let's do fluorine because the electron configuration is nice and easy. Fluorine has an electron configuration of 1s2, 2s2, 2p5. Right now, how many valence electrons does it have? It has 7. It is 1 away from having a full octet, a full shell. It only needs 1 more, so it wants 1 more. It's going to tend to try to get that 1 electron to fill up its shell. Oxygen is 1s2, 2s2, 2p4, right? And it's going to be, it's pretty close as well. It's only got a couple away. So what's going to happen is, this is actually why nonmetals tend to gain electrons. If we look at the nonmetals are over here. Now, this stair-step line is here, right? And nonmetals are to the right of it. So nonmetals over here, what makes nonmetals behave the way they do is they're close to 8 valence electrons. They're really close, right? So they just need a few more, right? Even so, fluorine, chlorine, bromine, iodine, they all just need 1 more to be like the noble gas closest to them. They all have 7 valence electrons. They just want that 1 more. So group 7A has 7 valence electrons. They need 1 more electron to be like a noble gas with 8 valence electrons. So, atoms with almost 8 valence electrons tend to gain electrons and become anions. This is why nonmetals do what they do, right? If we go back and we look at the metals over here, right? Metals are all over here. They have, we're going to sort of ignore the transition metals right now. The nonmetals over here, the metals over here don't have very many valence electrons at all. 1, 2, and 3, because remember our stair-step line is like right here. They tend to form, well, let's think about it. Let's look at the electron configuration of, say, lithium. Or we could even go with, actually, let me do it this way. I'm going to do the electron configuration for sodium and magnesium, both. All right. So they're very similar. Sodium is going to be neon 3s1. Magnesium is neon 3s2, right? So they want 8 valence electrons to be like argon. However, sodium has 1 valence electron, right? Magnesium has 2 valence electrons. They are both, sodium is 7 electrons away from being like argon, sorry. And magnesium is 6 electrons away. It's a lot of electrons to gain. It would be much easier for sodium just to give up this 1 electron and then now have 8 and drop down to exactly the same electron configuration as neon. Magnesium could give up 2 and drop down to the same electron configuration as neon, right? But this would make them sodium plus 1 and magnesium plus 2. So metals, because they don't have very many valence electrons, their only real recourse to get to being like a noble gas is to lose electrons and become cations, right? So this is really common among metals. So the octet rule actually tells us how many, and I sort of alluded to this already. And I think it becomes really easy if we just look at the periodic table. Remember, you'll be given a periodic table for any exam or quiz. So if we look here, right, fluorine, chlorine, bromine, iodine, these all have 7 valence electrons, right? To get to 8, they just need 1 more. So this group tends to form charges of, oops, I'm writing a plus for some reason, -1, right? Because they want to gain 1 electron and be -1. Their charge will tend to be -1. Now, if we go one group over here, oxygen, sulfur, selenium, tellurium, they have how many valence electrons? They have 6 valence electrons. They need 2 more to be like the noble gases. So they're going to try to gain 2 and become -2. Right? Nitrogen, phosphorus, arsenic, they are 3 electrons away. They have 5 valence electrons. They need 8, so 3 more will get them there. Now, you might say carbon, silicon, germanium, they're right in the middle. They have 4 out of 8. Now, I'm going to come back to them. I'm going to talk about them in just a little bit. But let's jump back over here. Let's jump over here. Hydrogen is a bit of a weird duck. Hydrogen, I'll come back to. I'm going to talk about this group excluding hydrogen. I'll talk about hydrogen by itself. Lithium, sodium, potassium, rubidium, cesium, francium, how many valence electrons do they have? Hopefully you said 1, right? They will want to lose that 1 electron, right? They'll get rid of their valence shell entirely and go to just having the next shell down. Beryllium, magnesium, calcium, strontium, barium have 2 valence electrons. They want to get rid of both of those for +2. And boron, aluminum, here, +3, right? It all has to do with how many valence electrons they have and how many valence electrons they're trying to get rid of, right? Or how many they're trying to gain or get rid of. Now I can go back to looking at group 4A, carbon, silicon, germanium. Technically, they could go either way. +4 for losing 4 electrons or -4. But really, both of these are pretty uncommon. It makes a lot more sense. That's a lot of electrons to gain or lose. That's a lot of energy. It's much more common for carbon or silicon to make covalent bonds. So we're going to talk about them mostly next chapter in chapter 5. So you don't see carbon +4 and carbon -4 very much, very occasionally. This being said, all of this, let me do hydrogen and then I'll get my caveat out. Hydrogen, it will tend to form +1 because it only has 1 valence electron. But also, if we look at its electron configuration, it's 1s1, right? It could lose the 1 electron, or it could actually gain 1 electron to be like helium. So hydrogen can go +1 or -1. So hydrogen belongs, more often than not, most of the time hydrogen ends up being +1. That's much more common. It can occasionally be -1. So hydrogen is a little bit like the alkali metals. It's also a little bit like the halogens. So hydrogen kind of has a split personality in a way, but it's more like the alkali metals, except it's not a metal. So there is that little conundrum. Now, one caveat I want to say, one thing to be aware of. When I'm talking about these charges, I'm talking about the charges that we see form in ionic compounds, because that's where I'm building up to. I don't mean to say that chlorine 2+ is impossible. It's not impossible. It will take a lot of energy and it will be unstable, but it's not impossible. So don't get totally freaked out if I ask you about a hypothetical chlorine +2. What these are for is this is for in a little bit when we start predicting ionic compounds. So I just want you to be aware of that. I'm specifically talking about in the confines of ionic compounds. So what I want you guys to do is pause this for a minute, and I want you to predict the most common ion formed by each element. So just predict the charge of what you'd predict based on its position on the periodic table, right? So aluminum is in group 3A. It's a metal. It's in group 3A. It has 3 valence electrons. It's easier just to lose those 3 valence electrons and become +3. Nitrogen. It's in group 5A. It has 5 valence electrons out of 8. It's over the halfway point. It's over that 4, so it's more likely to gain electrons than lose them. It needs 3 more to have 8, so it is -3. Chlorine. Chlorine has 7 valence electrons. I know this because it's in group 7A. It needs 1 more electron to have its 8, -1. Rubidium. In group 1A, therefore, has 1 valence electron. It wants to lose that 1 valence electron and become +1. Magnesium is in group 2A. It has 2 valence electrons. Therefore, it wants to lose those 2 and become +2. This is important that you're able to do this, so you're able to predict these. Now, one last word of warning. We're not going to try to predict the transition metals at all. We're not going to try to predict them. They do form ions, but because of some wackiness with the d electrons, the charges they form are very strange indeed. So we're not going to worry about them. I will talk about them a little bit later when we do naming.